So today we're going to be talking about mesh analysis. Mesh analysis is very similar to nodal analysis, except instead of applying Kirchhoff's current law multiple times, we're going to be applying Kirchhoff's voltage law multiple times. So we're going to learn this technique by looking at a series of different circuits. And the first one that we're going to look at is this guy right here. So let's say that we have a 10-volt source. A 9-ohm resistor. A 2-ohm resistor. A 1-ohm resistor. 7-ohm resistor. I'm going to put a dependent source in right here. And let's have this be 3 Vx. Here we will have a 4-ohm resistor. An 8-ohm resistor. Here's a 5-ohm resistor. Here is a 6-ohm resistor. And I'm going to adjust my notes and make this one a little bit more difficult than I usually would. And by that, I'm going to assign my voltage Vx in kind of an odd place, which you'll see me do things like this on your in-class assignments and your exams fairly regularly. Just letting you know I'm still a jerk. All right. So much like we did with nodal analysis, we are going to develop a algorithmic approach or a series of steps that we should carry out in order to solve a circuit like this. Okay. So our first step is going to be to identify our meshes. So this green path here is going to be mesh 1. This blue path will be mesh 2. And this red path will be mesh 3. So I do want to point something out really quickly here. Right now, since this is our first introduction, I'm being very deliberate about identifying our meshes. Later on, I will probably lump steps 1 and 2 together. And so that would look something, actually, let me tell you what step 2 is first, and then it'll make more sense. Step number 2 will be to assign mesh currents. So I could say that there is some mesh current IA flowing around this green path, some mesh current IB flowing around the blue path, and some mesh current IC flowing around the red path. Now back to what I was saying a moment ago. I'm not going to intentionally draw things out in this detail later on. I'll probably do it for the rest of the day, but later on you might see me do something like this as my mesh current IA is effectively what this designates is that I assume that my mesh current IA is flowing in a clockwise direction around whatever mesh I put that little loop thing in the middle of, okay? It's the same notation. Just wanted to make you aware of it. All right, so one thing that I want to point out here is that I have assumed that all of my mesh currents are going to be flowing in a clockwise direction. We do not have to make this assumption. They could all be flowing in a counterclockwise direction. You could have some flowing in a clockwise, some flowing in a counterclockwise. That being said, your life will be much easier if you choose to use all clockwise or all counterclockwise, because you won't get random positive and negative signs where you wouldn't necessarily expect them if you followed one convention, okay? So the direction that you choose for the meshes is entirely arbitrary, but for the sake of making as few mistakes as possible, it's best that you choose one particular direction to put all of your meshes in. You don't have to, but the algebra can get more confusing if you choose not to. All righty, so our third step is going to be express our controlling variables in terms of our mesh currents. So what I'm about to depict here in this orange color is one possible way. I would argue it's the best way for this particular situation for us to determine what the voltage Vx is in terms of our mesh currents. And so recall that Kirchhoff's voltage law does not require me to use paths where current is flowing through them at all points, right? Kirchhoff's voltage law is simply the sum of the voltage drops around some closed path. So if I were to start here at the negative polarity terminal for the voltage Vx, go across, come down like this, and come down like this, I could say that negative Vx plus, now I have to take into account the voltage drop across the 4 ohm resistor, okay? So what I'm going to do is I'm going to use Ohm's law here. So it's a 4 ohm resistor, so that's going to be 4 ohms. And now I have to figure out what the total current flowing through the 4 ohm resistor is, where the positive polarity is on top, or assumed to be on top, and the negative polarity is assumed to be on bottom. So we're saying negative Vx plus the voltage drop over the 4 ohm resistor plus the voltage drop over the 3 ohm resistor is going to be 0, okay? So I want the total current flowing down through the 4 ohm resistor expressed in terms of my mesh currents. IA minus IC. Thank you very much. Kevin, how did you come up with that? Yep. You're 100% correct. So what Mr. Parnell observed is exactly what we are going to do, okay? So we're looking for the total current with a direction down flowing through the 4 ohm resistor. As the green mesh current IA flows around its clockwise path, it flows down when it hits the 4 ohm resistor. So since it's in the same direction as the current we're looking for, it gets a positive sign. As the red mesh current IC flows through the 4 ohm resistor, it is flowing up or in the opposite direction of what we're looking for. So we give that part a negative sign. The total current flowing down through the 4 ohm resistor is then simply IA minus IC. So we're going to do something similar for the 6 ohm resistor. we want the total current flowing through the 6 ohm resistor in this direction. Anybody have any thoughts on how we might express that in terms of our mesh currents? Six times negative IC. Thank you, John. That's also correct. So I'm going to call this negative 6 ohms times our mesh current IC. And then with a trivial amount of algebra, we can see that Vx is going to be 4 ohms times IC, excuse me, IA minus IC minus 6 ohms times IC. That is about as hard as expressing a controlling variable can be in a mesh analysis problem. And you guys knocked it out of the park first try. So that's great. If that didn't make sense, by all means, please let me know, and I would be happy to explain it again. But if everybody is comfortable with it, we can move on to our next step. All right. So step number 4 will be to write a Kirchhoff's voltage law equation for each mesh. So effectively what we're going to do is we're going to follow our mesh current around its clockwise path. And we are going to assume that the mesh current we're following is going to flow into the positive polarity terminal of any resistor that we see. Okay. So let's start by writing a KCL equation for mesh A. Excuse me, KVL around mesh A. Okay. And I'm going to start in the bottom left-hand corner because that's where I start. I like to start writing my Kirchhoff's voltage law equations. So what's the first thing that I see? The voltage source. Okay, so the 10-volt source. Do I see the positive polarity terminal first or the negative polarity terminal first? The negative. So I write negative 10, just like we did when we were doing Kirchhoff's voltage law equations on our second day of class or whatever it was. Okay. What's the next thing that I see? The 9 ohm resistor. So I will have plus 9 ohms. What's the total current flowing through the 9 ohm resistor in the direction of mesh current IA? Just IA, right? There's no opposing current because it's on the perimeter of the circuit. As we continue to follow our mesh current IA, what's the next thing we see? The 2 ohm resistor. What will be the total current flowing through the 2 ohm resistor? IA minus IB. And then we see our 4 ohm resistor, which the current flowing down, we already know to be IA minus IC because we use that when expressing our controlling variable. And then lastly, we see our 5 ohm resistor, which carries a current of only IA since it's on the perimeter of the circuit. And then we set this equal to 0. That's as hard as mesh analysis has to be. We're just going to do that 2 more times. John, how may I help you? Yes, I could have. The reason why I didn't use the other, the triangle to the top right is because Vx wouldn't have then been expressed only in terms of mesh currents. So if I had used the other triangle there, I would have had negative Vx plus 3Vx plus 8 IC is equal to 0. And that should be able to be solved. but I wanted to illustrate the concept of total currents and all that kind of good stuff. Technically speaking, literally any loop that includes that voltage drop Vx can be used to solve for Vx or express Vx. So I just chose a small one that would help me tell you guys what to do in later steps. Okay, so does anybody have any questions with regards to our Kirchhoff's voltage law equation for mesh A? This hopefully seems fairly straightforward. You guys are picking up on it really quickly, which means one of several things. A, I'm an awesome teacher, or B, this is pretty easy. I'm leaning towards B. All right, so let's look at KVL at mesh B. So now we are going to follow mesh B around its clockwise path. So I'm going to start here and head up. So the first thing that I see is the 2 ohm resistor. What is the total current flowing up going to be? IB minus IA, absolutely. Then we see the 1 ohm resistor. Sorry. There's only a single current flowing through it, just IB. Then we see the 7 ohm resistor. And again, there's only one current flowing through it, IB. And then we see our dependent voltage source, because we see the negative polarity terminal first. It's going to be negative 3 Vx. We set that equal to 0, and we're done. Anyone have any questions, comments, or concerns with regards to our Kirchhoff's voltage law equation at mesh B? All right. So finally, we will write a KVL equation. For mesh C, starting at the bottom left-hand corner. Goodness, that's not what I meant to do. Here. So heading up, the first thing we see is 4 ohms. We have a total current of IC minus IA. Next, we see the positive polarity terminal of our dependent source. So we're going to have 3 Vx. Then we see our 8 ohm resistor, which only has a single current of IC flowing through it. Then we see our 6 ohm resistor, which only has a single current of IC flowing through it. And since we've got all 4 terms, we set it equal to 0, and we are done. Kevin, did you have a question? How do you mean you can get rid of 2 of the equations right off the bat? Mm-hmm. So there's not a, so you're saying there's not a contribution of IB anywhere in?
Well, no, I'm saying you can solve it just because you using.
Yeah, that's very true. Actually, I disagree with that wholeheartedly. Right, because so I see what your logic is there. So what Kevin has noticed, let me write some things down here. Is that this equation right here and this equation right here only contain IA, IC, and Vx, but there isn't a third equation that only contains IA, IC, and Vx, or yeah, Vx. So our mesh current A contains, or excuse me, our KVL at mesh A expression contains IA, IB, and IC, but no VX. And our KVL at mesh B expression contains IB, IA, and VX. So we're still gonna have to use all four, yeah. But no, there will definitely be times where you can observe that you have two equations that only feature two variables, and so you can kind of just throw away things to solve for those, but this is not one of those cases. We're actually going to wind up using all four. All right, so at this point, we're on to step 4, which is simply to solve our system of equations. Excuse me, step 5. And this is simply calculator / computer work, okay? So I'm not going to waste your times doing that part because that's the exact same thing that we were doing at the end of class on Wednesday, literally just putting the equations into our calculator and then whatever the results that came out of it are the results, right? So there's no real benefit to going through that and wasting 10 minutes and putting this into our calculator. All right, so much like we did with nodal analysis on Wednesday, we are now going to break things to some extent by including current sources this time. So we are going to consider the following circuit. And I'm going to define my controlling variable Ix to be this current, like so. So instead of making you guys suffer through the errors that are going to happen when we try to apply mesh analysis exactly like we did for the first problem, and then deriving our two additional steps, I'm just going to talk you through them as we get to them, because you'll have a better understanding of where they come from, having seen how we did it with nodal analysis. So in the case of circuits that contain current sources, we are going to, again, add 2 more steps to our system, or to our process here. So our first step is still going to be identify our meshes. Like so. We are then going to label our mesh currents. So let's call this guy IA, red IB, blue IC, and orange down here will be ID. Step number 3 will still be to express our controlling variables in terms of our mesh currents. This one should be a little bit easier than our last example. Would anybody care to take a crack at it? Who agrees with John? He said IX is equal to ID minus IC. So Jackson, Tyler, Hannah. More people should agree with him. He's right. So you could, but we're going to handle that next. So that's a fantastic thing that Kevin is asking about. So I'm going to write this down. IX is equal to ID minus IC. The reason for that is that ID is in the same direction as IX as it flows around its clockwise path. IC is in the opposite direction as IX as it flows around its clockwise path. Things in the same direction get plus signs, things in the opposite direction get minus signs. Okay. So what Kevin was just asking about takes us to step number 4. This is going to be one of our new steps. We need to write current relationship equations for each current source. Does not matter if it is a dependent current source or an independent current source. So, Kevin, since you already brought it up, how do I express the current that's being provided by the 6 amp source in terms of our mesh currents? You're absolutely correct. So Kevin has also observed something interesting here. Anytime we have a current source on the edge of the circuit or at the perimeter of the circuit, we are effectively just told what that current, that mesh current is, right? There can't be any current in opposition to ID or any mesh current in opposition to ID. So we just have a simple relationship that ID is equal to 6 amps. With our interior current sources, like the 5 amp source here in the middle of the circuit, we have to be a little bit more careful because there will be 2 opposing mesh currents, right? So there will be one mesh current that is in the same direction as the current source. And if you do everything all clockwise or all counterclockwise, there will be one mesh current that's in the opposite direction. So Hannah Riddick, I'm going to pick on you. How do I write my current relationship equation for my 5 amp source there in the middle? Yes, ma'am. There's 2 current sources, so there's going to be 2 current relationship equations. So the 5 amp current source is shared between the A mesh and the C mesh. So it's going to involve mesh currents IA and IC, and that's it. So the mesh current IB flows around this clockwise path in this bottom left-hand corner. How would any part of IB, which is just circulating around that square loop, go off to that other branch? Yeah, so it's confined to that little bottom left-hand path. Similarly, the orange current is confined to that little bottom right-hand path. So the only things that should contribute in terms of mesh currents to that 5 amp is the mesh current IA and the mesh current IC, because the 5 amp source is literally shared by mesh A and mesh C. So which of the two mesh currents are in the same direction as the 5 amp source as it travels through that branch of the circuit? IC, so that's going to get the positive sign. And by process of elimination, and also because we can observe it, IA is going to get the negative sign because IA is flowing from right to left as it passes through that 5 amp source, which is in the opposite direction. Okay. All right. So now we move along to step number 5. We're going to write a KVL equation for all super meshes. So that requires me to explain to you all what a super mesh is, okay? So not going to go into a great amount of detail here, but if we were trying to write a KVL equation around mesh A, we would run into a problem as soon as we try to express the voltage drop over our 5 amp current source in terms of our mesh currents, because it literally cannot be done. Just like we couldn't write a KCL expression for the current flowing through a voltage source because they're not related, okay? So instead, we are going to combine two meshes to create a path that avoids us having to take that voltage drop. We want to make the smallest possible combination of meshes that avoids taking that voltage drop. So I'm going to draw that in purple here. So we're going to follow IA along this portion of its path. Once we get to that little branch that contains the 5 amp source, we need to choose a different direction. So I'm going to go down. And now we can get back to our original path, okay? So our super mesh is going to be the smallest combination of meshes that encloses the interior current source so that we don't take the voltage drop over the interior current source, okay? We also have to make sure that our super mesh doesn't contain any perimeter current sources either, because if it did, we would be having the same problem, right? So this purple path is going to be our super mesh path, and I'm going to call it super mesh AC because it contains the meshes A and C. Quarterback, right? So we're going to now write a Kirchhoff's voltage law equation around super mesh AC. So we're going to start from this bottom left-hand corner, and we're going to follow the purple path. So what should our first term be? Ten times IA. Absolutely correct. Thank you. What should our next term be? So 4 times IA minus ID. All right. What do we see next following the purple path? 5 times IC minus ID, absolutely correct. What comes next? -2 IX. And then our last term will be somebody other than John. Three times IA minus IB. Thank you very much, Tyler, I think, yes. And we set this equal to 0. That's our only super mesh in this circuit. So we can now move along to our last couple of steps here, okay? Step number 6 will be to write a KVL equation for all remaining meshes that do not contain a perimeter current source, right? And so what I mean by that specifically is we're not going to write a KVL equation for our mesh ID. The only equation that we need from that particular mesh is this one right here. We can't write a KVL equation actually for it because it would involve taking the voltage drop across that 6 amp current source. So the only mesh that we haven't written an equation for effectively is mesh B. So that's our last step before we solve. So starting down here, we're going to have -4 plus, then we see our 3 ohm resistor, and that's going to be carrying a mesh current of IB minus IA. Then we see the positive polarity terminal of our dependent voltage source, so we're going to have twice IX. That's our last term. Set it equal to 0. And then finally here, step number 7 will be to solve our system voltage. So we are not going to bother solving the system because that is a fairly straightforward process. One thing that I do want to point out to you guys, because I get asked this question a whole heck of a lot, is that 2 ohm resistor there that's in series with the 5 amp source. It never showed up in any of our equations. Is that a problem? And the short answer is no. Okay. So what we did with our super mesh is effectively the exact same thing we did with our super nodes in the last class. We simply effectively wrote a KVL equation around mesh A, wrote a KVL equation around mesh B, and added the 2 of them together so that the voltage drop over the 2 ohm resistor would have been taken into account positive polarity on the left and positive polarity on the right. And when we added them together, it got canceled out. The 2 ohm resistor does not need to be in any of our equations. Okay. All right, so let's do one last thing real quick here. And this is going to be much, much shorter. I just want to show you guys what happens when we wind up having overlapping super meshes, if you will. So let's look at a fairly straightforward circuit. Let's say that we were going to try to use mesh analysis to determine the value of this current right here, Ix, okay? Not going to write down all of the steps or anything like that. We're just going to go through them this time. So I'm going to call this guy mesh current IA, and I'm going to call this guy mesh current IB. There are no dependent sources, so we don't have any dependent or controlling variables to write an equation for. So now we can move along just to our current relationships, right? So what are our current relationship equations going to look like? So IB, I'm going to write it the other way around, just not to be argumentative, but I usually write the current provided by the source is equal to some combination of mesh current. So I'm just trying to be consistent with how I would normally do it. What's my other equation going to be? So 3 amps will be equal to IB minus IA. All right. So now I would get around to writing KVL equations, except that I can't. There's no way that I can combine these meshes that doesn't involve taking the voltage drop over a current source. Is this a problem? No, because I only had 2 meshes and I already have 2 equations. I don't need to do anything else. I'm just making more work if I'm trying to continue on, okay? So if you ever have effectively a interior current source that's touching a mesh that contains a perimeter current source, you don't need to write a KVL equation at all for that. The current relationships take care of it. That's the only thing that I wanted to point out, because you're going to see that on the in-class assignment at least once, and you're definitely going to see it a couple of times in your homeworks, okay? So in a situation like this, where this could have been part of a larger circuit, you're limiting the number of KVL expressions that you have to write. So having multiple current sources in a circuit that you're trying to do mesh on is usually a good thing. Just like having a lot of voltage sources in a nodal analysis circuit is usually a good thing as well. It means you don't have to write as many equations, you don't have to write as many Kirchhoff's law equations. You just get simple relationship equations instead. So, all right, that is enough out of me for the day. Your in-class assignment, I believe, is 3 problems. If you need any help with it, please let me know. I'm going to chill here instead of floating around the room because I don't feel particularly well. So just raise your hand and I'll put my mask on and come help you out if you need it.